Hello, student. Uh, so we have got our ladder circuit, which consists of capacitors and inductors. Okay. So we have calculated those values using that 3 steps. Okay. Uh, so first we have calculated the filter order. Then we have calculated the prototype capacitance and inductance value using the table or using this equation. Then we have scaled them to our impedance and for required frequency. Okay. So finally we got this ladder circuit. Okay. So this is our LPF actually. So this is our low pass filter. Okay. And I have approximated this capacitance and inductance value to the third decimal point. Okay, but if you are doing this calculation by your hand using a calculator, you can approximate up to 2 decimal point. That will be okay. Okay. So now we are going to implement this ladder circuit. Okay, so we know that when the frequency is very high, this capacitance and inductance value will be very low. So maybe practically it is difficult to find these capacitors and inductors in the market. Okay, and also if we use these lumped element, these capacitors and inductors, then when we are soldering these things, sometime again the impedance and the calculated value can be changed. Okay, so that LPF design may not be very reliable. Okay, so we are using another method. Okay, that is called step impedance method, or sometimes it is called distributed elements technique method. Okay, so we are going to implement our LPF design using this technique. Okay, using this technique. Okay, actually here we are going to use microstrip line. Okay, here we are going microstrips. That is a sort of transmission line. Okay, microstrip line section. Okay, microstrip line section to represent or to work as inductors and capacitors. Okay, inductors and capacitors. Okay, capacitors. Okay, so we will see how to do this. Okay, and before that I will give you a very brief introduction about the microstrip line. Okay, I think you know that microstrip line consists of, actually this is called substrate. Okay, this board is called the substrate board. Okay, so here we have one copper layer. Okay, here we have one copper layer and another copper layer. Okay, so these are copper layers. Okay, and between these two copper layers we have a dielectric material. Okay, so we have a dielectric material. Okay, so this is a substrate. Okay, so there are many substrate. Okay, that can be used for high frequency design. Okay, so you are given Deltec substrate, okay, to do your design, okay. Actually we use this substrate to make microstrip, okay, microstrip line, okay. So microstrip is nothing but this kind of copper section, okay, copper layer, okay. So this bottom copper layer act as the ground terminal, okay. So this will be the ground terminal, okay, and this will be our line, okay. So we feed the signal to this transmission line, okay. So this is a transmission line. We have a line section, okay, and we have the grind section, okay. So there are many parameter related with this microstrip, okay. So one is the impedance, okay. One is the impedance, maybe characteristic impedance of this transmission line, okay. So it is mainly depend on the width of the transmission line, that is this width of the microstrip line width, okay, and also the thickness of the dielectric material. So this D is the thickness of the dielectric material, okay. So this is D is the thickness of dielectric material, and also it vastly affected by the dielectric constant, permittivity, relative permittivity of this dielectric material, okay. So these three parameters are mainly influenced on the characteristic impedance of this transmission line, okay. So it is given, so there are many equations, okay, but we can use this equation to calculate the so we can use this equation to find width, okay, width, or so normally D is given, okay. So we are given the dielectric constant thickness, that is this, okay. So this is the D, okay. It is normally given, okay. And if it is given, and if we know the impedance, characteristic impedance, we can calculate the width, okay, using this equation. And also there are some analysis formulas. These are synthesis formulas, okay. So using this, if the epsilon r, the relative permittivity, and the impedance is given, we can find the dimension using this synthesis formula. And there are some analytical formulas, okay. So that those formulas can be used if we are given this W and D dimension, we can calculate this Z naught, okay, Z naught and other parameters, okay. So that analytical formulas are not required for this design, okay. So I am not going to present them here, okay. But I think you have given those formulas, no? Okay. So anyway, we will use this synthesis formula, okay, to calculate this width and this width, okay, because we are given the thickness, okay, and also we are given this epsilon r, okay. So that is this relative permittivity, that is epsilon r, that is also given for this dielectric material, okay. For this dielectric material, it is also given, okay. So we know this D and epsilon r. So if we know the impedance, okay, if we know the impedance, we can calculate this width. Okay, so we have to calculate the width of the transmission line, microstrip line. Okay, and so I think you know that if a wave is, if an electromagnetic wave is traveling on in free space, okay, so that velocity is given by 1 by square root mu naught epsilon naught. Okay, so this is permeability. Okay, and this is permittivity, and this is related with the magnetic fields. Okay, magnetic field. This is related with the electric field. Okay, electric field. Okay, and if we know this value, we can calculate the velocity of a electromagnetic wave in free space, and it is we can get 3 to the 3 into 10 to the power 8 meter per second. No, so this is the velocity. Okay, and so this velocity is if the electromagnetic wave is traveling in the free space. Okay, but if this electromagnetic wave is traveling on another material, in another material, okay, so we can say that is equal to mu naught mu r, okay, and epsilon naught epsilon r. Okay, so any dielectric constant, this mu r is normally very similar to 1. Okay, it is very near to 1. Okay, so we can ignore this mu r. Okay, and you have to only consider this epsilon r only. Okay, so in other words, okay, so if you substitute this v naught with this, okay, assuming that mu r is equal to 1, you can get Vg is equal to V naught divided by root epsilon r. Okay. So this is the, if the wave is propagating in another medium, okay, so this will be its velocity, and this is called guided velocity. No, this is called guided velocity. Okay, and we can simplify it by dividing V naught from epsilon r. Okay, but in the case of microstrip, okay, you can see that so wave is propagating through this material, through this copper plate. Okay, so here you have the electric permittivity, relative permittivity epsilon r, and here you have the air. No, in this side you have the air. Okay, so you can see that this wave is traveling between epsilon r and air. Okay, so relative permittivity for air is 1. Okay, so you can see that if we consider the microstrip, okay, if we consider the microstrip line, this the epsilon relative permittivity for that wave is between this 1 and epsilon r. Okay, actually that is called epsilon effective permittivity. Okay, and so if you find the wave velocity, okay, if you find the wave velocity in the microstrip line, okay, in microstrip line, in microstrip line, okay, in microstrip line, you have to use this epsilon effective, not epsilon r. Okay, so the velocity, the guided velocity of in the microstrip line will be V naught, velocity in free space, divided by epsilon effective. Okay, epsilon effective. Okay, so you can see that you know that V is equal to F lambda. V is equal to F lambda. So this lambda also influence with this epsilon r effect. Okay, so in a microstrip, okay, the guided wavelength can be written. So you can use this V equal F lambda and this identity, and you can very easily prove this. Okay, the guided wavelength is equal to lambda naught, that is the wavelength in free space, divided by square root epsilon effective. Okay, so we have to use this one also. Okay, so to find the guided wavelength, also you can find the epsilon effective. Okay, so this epsilon effective is mainly depend on the width of this transmission line and the dielectric thickness. Okay, and also with the epsilon r. Okay, so this epsilon effective is also given by another equation. Okay, yeah, I have insert that one also, this one. Okay, okay, so if you need to calculate epsilon effective, you can use this equation. Okay, so if you carefully look at this equation, okay, you can see that this epsilon effective is depend on epsilon r, and also with width, and also with d. Okay, so you can see that epsilon r is constant for a certain dielectric material. For certain substrate, this epsilon r will be constant. Okay, and also this d, okay, dielectric thickness also will be a constant. No, okay, but okay, for different transmission line, this width can be changed, because this width, okay, so we are using different, we are going to use the transmission line with different impedance. Okay, different characteristic impedance. Okay, different impedance. Okay, different impedance. And if we are going to use different impedance, for different impedance, we will get different width value, different width. Okay, so width of the microstrip line is directly related with the characteristic impedance of this transmission line. Okay, so if we have different impedance value, we should have different width related with those different impedance value. Okay, so this different, for different width, we will get different epsilon r, effective epsilon r, effective permittivity. We can get different effective permittivity we will have for different width of transmission line. Okay, okay, so so this knowledge you should have to design this step impedance design. Okay, okay, so we will start. Okay, so the first one is, okay, so first step is actually this is also another theory. We can prove this. Okay, we can prove this, we can approximate this. Okay, we can approximate high impedance line. Okay, high impedance line is represent a inductor. And low impedance line will represent the capacitor. Okay, so high impedance line, you know that if the impedance is high, the width should be low. Okay, and for low impedance value, because the transmission line impedance is low, width should be high. Okay, so you will get for capacitors, okay, you will get for capacitors, okay, some transmission line with wider transmission line, and you will get a narrow transmission line for inductors. Okay, narrow transmission line for inductors. Okay, so we will see that. Okay, so first we have to consider, we have to assign some appropriate inductance impedance value for these inductors and capacitors. Okay, so here we are given that data. Okay, so we are asked to get high impedance value as 90 ohm, low impedance value as 20 ohm, and characteristic impedance of feeder lines are 50 ohm. Okay, so we are given all required impedance value. Okay, so what should we do? We should first calculate the width related with these impedance value. Okay, so you can use this synthesis formulas to do that part. Okay, to do that part. Okay, this synthesis formulas you can use. Okay, no issue. Okay, so you can see that we are given relative permittivity epsilon r, and we are given the dielectric thickness d. Okay, so using this value, using epsilon r, and you are given also the impedance. Okay, so you can first calculate the width for high impedance line. Okay, let's say that is WH, width for high impedance line. Okay, so if you want to calculate the WH, that means high impedance line width. Okay, so you are given this epsilon r and the high impedance value. Okay, so you can substitute 3.2 instead of this epsilon r, and 90 instead of this Z0. Okay, and you can calculate the A value. Okay, you can calculate this A value. Okay, and also you are given the epsilon r and Z0. So here you can put 90 and you can put 3.2. Then you can calculate the B value also. Okay, so now you have A and B values. Okay, so by substituting this A and B values, you can calculate W by D. Okay, you can calculate W by D. Okay, you can calculate this value. Okay, then you know this D, you know this D, the thickness, it is also given 0.762 millimeter. Okay, so D is 0.762 millimeter. So you can calculate the WH value. Okay, in the same manner, you can calculate the low impedance line with WL. Okay, and in the same manner, you can calculate the transmission line width. Okay, so that transmission lines are used to feed the signal to the low pass filter. Okay, and you can also calculate the transmission line width. Let's say that is omega naught. Okay, so these three value you can calculate it using this synthesis formula, and you can also note that here we are given two separate equation for separate condition. Okay, so after calculating this A and B value, still we don't know the W divided by D value will be less than 2 or greater than 2. Okay, so what we have to do? So you have to first substitute this A values and B values. Here only A values actually. You can substitute the A values here and you can see that W by D is greater than 2 or less than 2. If it is less than 2, you can use that value and you know the D and you can calculate the W. Okay, but unfortunately, if this after you assign A value and calculated this value, okay, if that is greater than 2, okay, you have to ignore that value and again you have to use this one. Then you have to also calculate the B and you can substitute it here and B be here. And if the A is there, you can the A is not there, no? Okay, so you have to calculate the B and you have to substitute B value to here and you have to calculate the WD ratio. Then once you calculate the WD ratio, you know the D value, you know this D value, then you can calculate the W. Okay, so you can use this synthesis formula like that. Okay, but in the lab session, as I told you, there are many online tool to calculate this transmission line width. Okay, so you can use this online tool, online calculator. You can just type microstrip. Okay, so if you can get that Cadence TX line tool, that is very good. Okay, but if you are if if you found it is somewhat difficult, you can use another microstrip line calculator. Okay, there are many calculators. Okay, for example, this may be a one. Okay, here, so you can see that this is so here you can see that this is a microstrip line. Okay, so this is the microstrip. Okay, and you can see that there is a thickness, very little thickness on this copper layer also. It is in micro level. Okay, but for the design, we no need to consider that thickness. Okay, so you can use that width. Okay, you can use that synthesis formula to calculate. Okay, so here dielectric thickness is given as H. Okay, and dielectric constant is epsilon r. Okay, so easily you can use this one. Okay, so what is our dielectric constant? That is 3/2. Okay, what is the dielectric height? That is 0.762. No, let's check. 0.762. 0.762. 762. Okay, so it is millimeter. And what is the frequency? Okay, the frequency is this frequency is not much affected to this width. Okay, but it is directly affected to the length, but the frequency is not affected to the width. Okay, but here I think you have to enter that now, that value also. Okay, but there is a little effect. Okay, so you can change the frequency and see how the width is changing. I think that width is changing very slightly. It is not affect much. Okay, so what is the frequency? That is 5.8. No, let's check. The frequency, always you have to use this passband edge frequency, that is 5.8 gigahertz. Okay, so we put that 5.8 gigahertz. Okay, so now you are going to calculate the WH high impedance value. Okay, so if you put 90, it is 90 ohm now, so you can calculate the width. I hope. happened? You have to also electric length value. Okay, so let's put 90, but it is not related with our calculation, but we have to put that value also. Okay, so if we put this value, okay, so you can see that we are given a width. Okay, we are given a width. Okay, and you can see that if I change this electrical length into 180, okay, you can see that this length will be around 16.6, but this width will not be changed much. Okay, let's see. So you can see that it is not changing. Okay, but you can see that this is doubled. Okay, this is double. So we have to put some value, but it is not affected to our width much. Okay, so you can put some value and you can see. Okay, so if I put 45, it will be 4 point something. Okay, but still you can see that width is not changed. Okay, so this, if you change this Z naught or epsilon r or dielectric constant, you can see that this width is affected very much. Okay, but for the frequency and electrical length, this is not affected much. Okay, so this is our high impedance line width. It is in millimeter, that is 0.615. I will put that is 0.62 millimeter. Okay, so now we have calculated. Okay, calculated the high impedance line. Okay, high impedance line width. Okay, line width, that is WH, that is equal to 0.62 millimeter. Okay, and this is related with 90 ohm, and we are going to represent inductors using this. We are going to represent the inductors using this. Okay, so we have calculated the WH value. Okay, now we have to calculate the low impedance line width. Okay, let's say it is WL. Okay, and it is related with 20 ohm. Okay, and it is for capacitors. It is for capacitors. Okay, so we can calculate the WL value using the same one. Okay, so I will put here 20. Okay, 20, and you can see that this width will be increased. Okay, because we are choosing a low value. Okay, low impedance value, so this width should be increased. So yeah, so now you can see that it is around 6.35 millimeter. Okay, so I will put it as 6.35. Okay, 6.35 millimeter. And also you have to calculate the transmission line width. What is the impedance for transmission line width? Transmission line, that is 50 ohm. Okay, so these are the transmission line, TX line. Okay, these are for TX line to feed the signal. Okay, so let's say that is W naught. So it is, you can calculate using the same one. Okay, so what is that? It is 50, no? 90, 20, and 50. So we have calculated WH. Now we have calculated the WL. Now we are going to calculate the W naught. Okay, width for 50 ohm impedance. So I put 50 here. Okay, and calculate. So it is around 1.8 millimeter, 1.83 millimeter. Okay, so I will use that one also. 1.83 millimeter. Okay, now we have calculated the width. Very easy. Now what is we have to do? Okay, so you can see that this width is to assign this microstrip section whether to inductor or a capacitor or a transmission line. Okay, so we have calculated this width. Okay, now you can see that we have different uh, capacitance value. Okay, capacitance value. Okay, so this capacitance value is directly related with the length of this transmission line section. Okay, for that parts, the length of the transmission line is important. Okay, so now we have calculated the already we have calculated the transmission line width related to different impedance value. Now we are going to calculate the transmission line length. Okay, line length. Actually, for transmission line, okay, for W naught, we no need to calculate the TX line section. Okay, so because this lines only used to feed the signal. Okay, so you can assume many practical value to the for transmission length. Okay, so let's say that it is around 7 millimeter. Okay, so I choose. Okay, so this is, you have freedom, you have the freedom to select this. Okay, so I use around 7 millimeter length for my transmission line section. Okay, so this is for transmission line to feed the signal, not for low pass filter. Okay, okay, now I need to calculate the length for high impedance length for inductance section. Okay, and also length for capacitance inductance sections and induction section are high impedance line, and capacitor sections, those are low impedance line. So we have to calculate these two lengths. Okay, these lengths. Okay, so you can use this. You can use this two identity. Okay, you can use this two identity. Okay, so you can use this two identity. Okay. So you can see that for given inductors value, you have to calculate, you have to use this formula to calculate the length of the inductor related microstrip section, and for given capacitor value, you have to use this formula to find the length for related capacitors line section, microstrip section. Okay, so you can see that there is you have to use the guided wavelength. Okay, lambda h and lambda l. Okay, so I have explained that when the width is changing, epsilon effective will be changed. Okay, so this will be lambda h is equal to lambda naught. You can find this using v is equal f lambda. Okay, so you know v, free space velocity, 3 into 10 to the power 8, and you know the frequency 5.8. Then you can calculate the lambda, and you have to divide it with related to epsilon effective related to high impedance line, because high impedance lines are very narrow, so epsilon effective will be different. And in the same manner, you have to find the guided wavelength for low impedance section. Okay, that is also lambda naught divided by epsilon effective related with to low impedance line. Okay, so So you have to use all these formulas to calculate the L. Okay. So what you have to do is, okay, so I have given the equation to do that one also. This is okay. Okay. I'm not going to explain this anymore because I have already explained this. Okay. So I will tell you the procedure. Okay. So what you have to do, you have to first calculate the epsilon effective related with the high impedance line. Okay, related with the high impedance line. Okay, so epsilon r you know, and high impedance line width you know. What is the width? High impedance line width, that is 0.62 millimeter. So you have to put this value, you have to convert this to meter and put this value here. Okay, put this value here, and you know the d, because this is d by 12, you no need to convert the units, because millimeter will cancel out. So this d will be 0.762, and you can put the width, and you can calculate the epsilon effective for high impedance line. Then you can use this formula. You know this value, and you know the lambda value, that is the lambda in free space. So you can calculate the lambda h, guided wavelength in high impedance line. In the same manner, you can put the low impedance width, that is 6.3, no, that is 6.35 millimeter here, and d already you know 0.762, and epsilon r is 3.2. Then you can calculate the epsilon effective related with the low impedance line. Okay, then you can calculate the guided wavelength in related with the low impedance line section. You can calculate this value and this value. Once you can calculate this value, you can directly put them here. Okay, so that value will not affect by the length. It is only affected by the w, d, and epsilon r value. Okay, so once you calculate that this value, it is constant. It is a constant. Okay. So how to calculate the inductance value? Okay. So length of the inductance you can calculate very easily. Okay. So you already know the lambda h. You have calculated that one. You can substitute that value here. It should be divided by 2.5, and you have to get the sine inverse. Okay. And this omega is the frequency, that is 2.5 fp. 2.5 fp means 5.8, and you have to put 10 to the power 9 because it is in gigahertz. Okay. So you know W, and this, what is this L? This L is the inductance value. Okay. So here we have 4 inductance value. 1, 2, 3, 4. Actually, we have 2 inductance value. 1, 2, because these are same again. Okay. So you have, if you can calculate the length related with this 2 inductance value, then you can calculate all the values. No, because this one and this one equal, this one and this one equal. Okay. So if you want to calculate the length related with this inductance, that is 1.85 nanohenry. Okay. That is 1.885 nanohenry. Okay. So you can, so this L is, that is, okay, 1.85 nanohenry. Nanohenry means 10 to the power minus 9. No, 10 to the power minus 9. Okay, then it should be divided by the ZH, that is 90. Okay, so you can calculate the L related with this inductance value. Okay, it is L2, and also you can calculate the L4. Okay, using this inductance value. Okay, using the inductance value, you can calculate the L4 also. So L4 is lambda h divided by 2.5 sine inverse 2.5 5.8, 10 to the power 9, 2.01 into 10 point minus 9 divided by 90. So you can calculate that value also. Then you can calculate the other values. Okay. In the same manner, you have to calculate uh, 5 lengths for this 5 lengths for these 5 capacitance value. Okay, actually there are 3 capacitance value, this one, and this one, and this one is equal to this one is equal to this one. So you have to calculate the length related with this. Okay, for that you have to use that second formula, this one. Okay, so you have to use this one. Okay, so what is that? Okay, so these are inductance value. Okay, so these are inductance value. Okay, so these are inductance value. And now we are going to calculate the capacitance value, capacitance length. Okay, so let's say this L1 is equal to lambda L divided by 2.5 sine inverse. What is that? Omega C ZL. Omega C ZL. Okay, so you can substitute the value here. So lambda L you have already calculated using this. Okay, 2.5 sine inverse omega is 2.5 into 5.8 into 10 to the power 9. And what is the C? The first capacitance is 0.838, no? 0.838 picofarad. 0.838 picofarad, that means 10 to the power 12 minus 12. And ZL, what is ZL? That is 20 ohm. So 20. Okay, so you can calculate the L1 value. In the same manner, you can calculate L3. Okay, so only this value you have to change. Okay, for that one, you have to substitute 1.342 here. Okay, you have to substitute 1.342 here. Others are same. This one same. This one same. This one same. Sine inverse. This also are same, and you have to calculate 1, 3, 4, 5. No, 342. 342 here. Okay, and 10 to the power 12, and it is multiplied by 20. Okay, so you can calculate L3, and same manner you can calculate L5. Okay, and you can calculate L7, that is this one you will get, and you can calculate L9 also, that is this one. Okay, the same value you will get. Okay, so you have to calculate only these 3 values. Okay, so you can calculate the length also. Okay, so let's calculate the length. Okay, so actually I also so maybe there may be the transmission, there may be I don't know, but there may be some developed length calculator, transmission line length calculator also, online length calculation. You can try that one. Okay, and if not, you can use that formula. Okay, so here I am in a usual, as in usual, I have coded it in MATLAB. Okay, so these are the things I know. Okay, so here I'm going to calculate the capacitance and inductance length. Okay, so I will uncomment this. Okay, so once I run this, I should have the capacitance length. This is for capacitance length. You can see that I have coded that equation here, lambda L 2.5 into sine inverse 2.5 FC ZL. Okay, in the same manner, I have coded the inductance length in MATLAB. Okay, so very easily you can code them. Okay, and what are the required values? You need ZH, that is 90, you need Z1, that is 20. Okay, so you need the relative permittivity, that is 3.2. Okay, so here I have directly insert the WD ratio for low impedance and WD ratio for high impedance. Okay, but here you can enter them. Okay, so that is one is WH. Okay, another is WL. We have calculated these things. Okay, and we can also enter the D value. Okay, D value. Okay, so what is the WH value? That is 0.62. WH is 0.62. So you can put this 0.62. Okay, and W8L value. So you can use the millimeter, no issue, because we need to get the ratio WH divided by D. Okay, so if we are going to get WH divided by D, you can see that the millimeter will cancel out. Okay, so we no need to convert the unit. Okay, so WH is 0.62. What is WL? WL is 6.35. 6.35, that is WL. And what is the distance? That is 0.762. No? 0.762. Let's check. Yeah, it is 0.762. Okay, and 3.2, 90 to 20. 0.62, 6.35. Okay, so we have enter all the values. No? 90, 20, 3.2, 0.62, 6.35, 0.762. Okay, now you can change this ratio. Okay, so this is for L. No? So that is WL divided by D. Okay, okay, and here WH divided by D. So I hope this should be work. Okay, let's see. Okay, so if I run this, okay, so you can see that in C1 I have put the capacitance length, and L1 I have put the inductance length. Okay, using that equation. Okay, so this is L1 capacitance length. Okay, so these are the capacitance length. There should be 4, no? Okay, there are 4 values. Okay, so I get the capacitance length. Now we have calculated all the parameters. Okay, so this is our capacitance length. Okay, so these are our capacitance length. Okay, sorry, inductance length. Okay, so these are our inductance length. Inductance length. Okay, and so you can see that there are 4 inductors. 1, 2, 3, 4. So you have 4 length. Okay, so that lengths are related with these capacitors, these inductance. So this length will be L2, L4, L6, L8. Okay, so this length we have already calculated. So this L is the inductance. Okay, here it is not the length. Okay, this L2 I put to represent the inductance L, and C is to represent the capacitor. See, here L2 is inductor 2, inductor 4, like that. Okay, I have name. It is only a naming issue. Okay, naming method. Okay, don't confuse. Okay, so anyway, I have calculated the length related with these inductors. Okay, So these are the length of the transmission line. So let's say that is L2, this is L4, this is L. So this is simple L2, L4, L6, L8. Okay. So this is related with inductor 2, inductor 4, inductor 6, and inductor 8. Okay. So you can see that this one and this one is equal, 4 and 6 equal, and 2 and 8 equal. Okay, 2 and 8 equal, symmetrical. Okay, so you can verify that our calculation is correct. Okay, so now we are going to we can get the capacitance value also, capacitance length also. So here it is in C1. Okay, so where is the C1 array? This one. So these are capacitance length. Okay, so these are capacitance length. There should be 5 length. Okay, because there are 5 capacitance. Okay, so you will see. Okay, so these are the capacitance length. Okay, capacitance length, capacitance length. Okay, so this is one length. Okay, so capacitance lengths also have a complex value. Okay, but you can see that the complex values are all the one complex values are 0. Okay, 0. Okay, but you can see that here you will have a complex value. Okay, but you can calculate, you can consider only the imaginary parts. Okay, imaginary parts. Okay, because sometimes these sine inverse values are not sine inverse value. Some for some phi value, the sine inverse value may be a complex value. Okay, so we have to ignore the imaginary parts, and we have to consider only this real parts. Okay, so there are 5 real parts, so you can assume them. Okay, so this one for, so these are in meter. Okay, so these are in meter actually. Okay, so these are also in meter. Okay, so you can convert it to millimeter by dividing by 1000. No, so if you consider, this will be 4.5 millimeter. 4.5 millimeter. So this length is 4.5 millimeter. This length is 1, 2, 3, 5.1 millimeter. This length is again 5.1 millimeter. This length is 4.5 millimeter. Okay, so you can write it in millimeters. Okay, so here if you consider this one, you can see that 1, 2, 3, 3.2 millimeter, 1, 2, 3, 6.7 millimeter. Okay, and this is 1, 2, 3, 7.7 millimeter, 7.7 millimeter. Okay, and this 6.7 millimeter, 6.7 millimeter, and this 1, 2, 3, 3.2 millimeter. Okay, and yeah, that's all. Okay, so you can see that this is for capacitance 1, this is for capacitance 3, this is for capacitance 5, this is for capacitance 7, this is for capacitance 8. And you can see that this one and this one equal, this one and this one equal. Okay, so this is L1, L3, L, this is the length. Okay, L5, L7, L9. Okay, so this is 9, L9. So we have calculated the width and the length also. Then how to design this? So you can make appropriate microstrip length in the substrate given substrate, okay, using this length and width. Okay, so you can see that if I draw the layout, okay, so it is like this. First you have the capacitor, that is high impedance, low impedance value, like this. Okay, so what is the width of this? 6.32 or something, no? Yeah, 6.35 millimeter. 6.35 millimeter. Okay, and then, okay, so it should have 3.2 millimeter length. Okay, then next one is the capacitor, sorry, inductor. So it should be high impedance value. That means that is the your length, the width should be very narrow. Okay, so what is that length? It is 0.62 millimeter. Okay, so it is very narrow, 0.62 millimeter. Okay, so this will be an inductor, copper plate. Okay, so these are copper plate, actually copper layers. Okay, so what is the length of that? That is 4.5, no, 4.5 millimeter, 4.5 millimeter. Okay, then you will have again a high impedance section, that is 6.35 millimeter width. Okay, so what is the length here? It is 6.7 millimeter. And you have a capacitor, sorry, inductor again, that is again 0.62 millimeter length width. Okay, 6.02 millimeter width. Okay, and what is the length? Length should be 5.1 millimeter, that is 5.1 millimeter. Okay, and you have a capacitor again. Okay, that is 7.7 millimeter, 7.7 millimeter. Then you have an inductor again, that is low impedance line, high impedance line. Okay, so what is that length? That should be 5.1 millimeter. Okay, that should be 5.1 millimeter, correct? No, 5.1 millimeter. Okay, 5.1 millimeter. Then again you will have a capacitor section like this. Okay, and what is the length of this capacitor section? That is 6.7, 6.7, okay, millimeter. Okay, and again you have a inductor, that should be 4.5 millimeter, 4.5 millimeter. Okay, okay, that's that one. This one, yeah, 4.5 millimeter. Again you have a capacitor. Okay, capacitor, that is 3.2 millimeter, 3.4 millimeter. Okay, so this will be your low pass design. Okay, and here you have in this side you should have a transmission line. Okay, that is for 50 ohm. Okay, that is for 50 ohm. So we select it as 8 millimeter or 7 millimeter. Okay, what is the width of this one? It is 1.8 millimeter. It is 1.8 millimeter, 1.83 millimeter width. Okay, and here also you will have a same transmission line section with 7 millimeter. Okay, so this will be your low pass filter design. Okay, so actually it is look like this. Okay, so it is look like this. Okay, So this will be the transmission line. Okay. And this is first capacitor. This is the inductor. This is second capacitor. This is the inductor. Third capacitor, inductor. Fourth capacitor, inductor. The last capacitor, and this is the transmission line. So this kind of design you will get. Okay. Okay. So we have designed that one also. What is your next task actually? So you have to draw this in. You have to draw this in HFSS. HFSS. Okay. So I will let you to do this, okay, by yourself, but it is very easy. Okay, what you have to do. So we have designed already BLC, branch line coupler. Okay, so same technique you can use to draw this one also. Okay, so I think you can do this like this. Okay, so first you can get appropriate, you can get you can draw a rectangle. Okay, first you can draw a rectangle. Okay, in HFSS you can draw a rectangle like this. Okay, you can draw a rectangle like this. Okay, and you can put it as copper. Okay, you can assign it to a copper. Okay, then you can draw another box, rectangle box here. Okay, here. Okay, here like this. Okay, you can draw a box. Okay, and that box, the thickness of that box should be 0.762 millimeter. Okay, what is this? This will be your dielectric material. Okay, so this will be your dielectric material. Okay, so now what you have to do, you have, so first one is your copper, the ground plate. Okay, the first copper layer is the ground plate. This one is the ground plate, and this one is the, then you have draw the box, that is your dielectric material. Okay, so top of the dielectric material, you can draw this copper section very easily. No, you can draw this. So so top of this dielectric material, you can draw this copper section very easily. How to do? You can use the rectangle and draw them. Okay, so you can use the rectangle and draw them. Okay, so you can see that. So once you get the length of this sheet, okay, you can get this value. Okay, so you can add them together. 7, 3.2, 7 plus 3.2 plus 4.5 plus 6.7 plus 7.7 plus 5.1 plus 6.7 plus 4.5 plus 3.2 plus 7. Okay, so you can get this length. Okay, okay, and you can put the same length here. Okay, for this section you can put the same length. Okay, let's say that length of this one is X, capital X. Okay, so you can draw a box, you can draw a sheet and a box with length X. Okay, X millimeter. Then you can draw your mm, your uh, your uh, this copper section in top of this. Okay, so first you can draw the transmission line, that is 7 millimeter. Okay, then you can draw the first capacitor. Okay, first capacitor, then you can draw the inductor. Okay, then your second capacitor. Okay, draw the inductor, third capacitor, draw the inductor. So you have to use the sheet. Okay, You have to use the rectangle and you can draw this very easily. Next capacitor. Rectangle 1, 2, 3, 4. And this is your next capacitor. Okay. So you can draw this somewhat. Okay. So I'm not good at drawing. Okay. Okay. So you can 7mm transmission line, your first capacitor, inductor, second capacitor, inductor, third capacitor, inductor, fourth capacitor, inductor, then last capacitor. Okay. Then a transmission line. Okay. So this will be 7mm. Okay. This will be 3.2mm length. This will be 4.5mm. This will be 6.7mm. This will be 5.1mm. This will be 7.7mm. This will be again 5.1mm. 5.1mm. This one, okay. 1.1mm. This will be 6.7mm. So this section again will be 4.5mm. This one will be 3.2mm and this will be 7mm. Okay. So you can very easily draw them and you can select all these section. Okay. Select all these section and unite them. Okay. Then you will get nicely. You can get a nice picture like this. Okay. Then here, so if you have drawn this in XY plane, okay, so you have to select the ZX plane. Yeah, ZX plane, no? So you are here XY plane, okay. So this is Y and this is X, okay. So if you are draw this in XY plane, okay, so you have to use the ZX plane, this plane, okay, to draw the boundary, to give the excitation, no? So you can draw that boundary like this, okay, and you can assign excitation from line to ground this way, and here also you can no, here you no need to put the excitation, only this side you have to give the excitation, no, because this will be the output. Okay, so you can give that one. Okay, so you can select the frequency. Okay, so you can select the middle frequency as gigahertz, 5.8 gigahertz, and you can get around 0.5 gigahertz to maybe 8 gigahertz range. Okay, then you can plot the S21 and S22. Okay, so you will get this kind of curve. You will get most probably this kind of curve. So see what are the value here and what are the value here at the 30 dB. So these should be matched with our pass band H frequency and stop band frequency. Okay, if not, you have to give some reasons to them. Okay, so that is your task. Okay, so I leave it to do in HFSS by yourself, but in case of if you have any problem or if you can't do it by yourself, you can ask me, then I can arrange another HFS session to do this design. Okay, okay, thank you.